Welcome to week 2. This video will cover chapters 4 and 5 in your textbook, with chapter 4 being the normal distribution and chapter 5 being standardization and z-scores. Chapter 4 also talks a little bit about sampling, which I wanted to take an opportunity to go a little deeper than just what's in the chapter. So to really set the stage for this week's reading, I wanted to say a little bit about sample and populations. So we went over a little bit of this in week 1. We talked about the population being all people we may be interested in, and we said that this could range from anywhere to the population being a classroom full of students, to the population being a university full of students, to a population being everyone in the whole world. So you can see the top part of this graphic, the population is defined as all of the people of interest in our particular scenario. So you can see from there what we do is we select a sample from the population, so a subset of that, and the sample are the individuals actually selected to participate in the research. So whether they're completing a survey, whether they're completing some kind of experiment, if they're participating in a focus group or a series of interviews, the sample are the actual individuals involved actively in the research. So we care about the people in the sample, but really the sample is a means for this last step on the left side of the graphic. We want to be able to generalize the results from the sample back to that larger population, whatever it may be. So if you think of something like medical research, let's say that we're going to run an experiment for a vaccine for a new drug. So we would want the vaccine to work on the entire population, so everyone in the whole universe, if you can phrase it that way. But that's not really possible in our experiment to obtain the entire population of everyone in the world. So we would maybe select a sample, some volunteers, and we would maybe divide them into two groups. Say one group gets the vaccine, the other group is a placebo group who does not receive a vaccine. So we care about the people in the sample and we want to know if the vaccine is effective, but ultimately our goal is to be able to generalize those results from the sample back to the larger population. So this is really an important process that underlies a lot of our research, whether it's in education. If you think about educational interventions, we want interventions that work on a large scale for all students, not just for a particular subset that might participate in our research. So this graphic's kind of a nice illustration of our research process and why it's so important to appropriately define our population and our sample. When we talk about thinking critically about research, we really want to be cognizant about what is the population and what is the sample. So as a little exercise here, I decided to pick on something that we have here in Omaha, which is a contest called the Best of Omaha. If you're really interested, you can Google it. You might already be familiar with it. But basically, this is a marketing study, if you will, put out by Omaha Magazine. And the idea is that people in the general population of Omaha can vote for some of their favorite businesses, whether it's a restaurant, a nail salon, a doctor's office, a recreational facility, those kind of things. And it's kind of a fun, I guess, exercise because businesses get really into it. They promote it. They really try to get people to vote for them. And then they get these yellow stickers that they can put on their business window to kind of signify that they won this award. So on the surface level, it seems like a good idea. It seems like a good marketing piece. But if we think critically about this from a research standpoint, we see that kind of our way of sampling from the general population of Omaha that there might be some flaws, and maybe you're already thinking about some. So to tell you a little bit more about the contest, not all businesses participate in it. It's kind of a pre-selected list of businesses, so it's not quite representative of every business in Omaha. And the people who are voters are either people who subscribe to Omaha Magazine or are people who have voted in the past and have received like email notifications. They're part of their subscriber list. So it really is only a select few people who actually vote on this. To add another dimension to it, a lot of times there's incentives to voting. So either a business might give away like a free appetizer in exchange for you voting, or even Omaha Magazine themselves will give away some prizes in exchange for your votes. So although it's kind of a fun contest and fun to have these bragging rights, from a research perspective, you can see how this sample of voters in this Best of Omaha contest may not be representative of the whole Omaha, Nebraska population. So that's just a good example of how we see these things either in headlines or in the news, and we really want to think critically about how was this study done, what was the population they're trying to generalize to, and how did they obtain their sample, and is there room for bias in that? So bias can happen in a number of different ways, like I pointed out, where the people come from, how they're incentivized to participate, who they are, and there's just endless things that we really want to be wary of. So especially when you're reading literature and journal articles, really pay close attention to where did the participants come from in their researcher's sample, and what might be some potential flaws or limitations to using this sample versus another. So some risks that we have with our sampling methods is kind of this first one here. The sample might not represent the larger population. So in my Best of Omaha example, the subset of people voting in this contest might not represent everyone in the Omaha area. And a lot of times, to lead to the second point here, we might not even know that that sample is misleading. So if you didn't do a little bit of Googling, you might not know where this data comes from, and you might not even think to kind of question the conclusions. And we might make decisions based on this bad information. So in this case, the stakes are pretty low. If I'm trying to figure out what the best Mexican restaurant is in Omaha, it's probably not going to hurt anyone if I go with the Best of Omaha recommendation. But if I'm really serious about this, I might want to seek out some multiple sources because I might have bad data based on the flawed sampling that they use. On the other hand, there's definite rewards to sampling. So as I've said before, it's really difficult to access entire populations in order to run a study. It would be really hard to try to talk to everyone in Omaha, Nebraska and ask them what their favorite Mexican restaurant is. So sometimes sampling is really efficient and it may actually do a good job of representing that larger population. If that's the case, then we can increase our level of confidence in our findings, and we can reach accurate conclusions at a very low cost. So from a statistics standpoint, we really want the most bang for our buck. We want to reach good, accurate conclusions by talking to as few people as possible. At the same time, we want to keep a little bit of an open mind because, again, we know that the samples can mislead us, but ultimately we think that we'll be able to make a wiser decision based on this available evidence and feeling good about the technique that we use to obtain our sample. So there's definite risks, there's definite rewards, and really when you're conducting your own research, the key is to just be transparent about those. So if you're writing a research article, this might be something that goes in your limitations section, where you address how you got your sample and what the possible pros and cons might be of that method, just so that the reader is aware and can kind of use a critical eye when they're interpreting your results in discussion. Here we have a couple of different sampling methods. These are also discussed in your textbook in Chapter 4. There are more sampling methods than these three, but these are probably the three most common ones that you see reported in research articles. So the first one, in kind of this bluish teal box on the far left, random sampling, this one is really the gold standard when it comes to experimental research. So you can see here the definition is selecting cases from a population in a manner that ensures each member of the population has an equal chance of being selected into the sample. So random sampling is really useful, and then on the other hand, it's actually difficult to do. So in order to make something truly random, we usually want to use something like a random number generator or a random number table. Even if you think about something like flipping a coin, that would be a good example of something random. But someone who says they're going to, stand outside of a shopping mall and randomly interview or survey people who walk by, that method isn't really random when you think about it, because you have a very specific subset of the population who might be at the shopping mall that day. These are people who have a vehicle that they can drive there. They maybe have some disposable income to go shopping and spend some money on fun things. It's not quite random in terms of representing the population as a whole. So random sampling is difficult, but the benefit is that we think that differences in individuals, things like personality differences, differences in levels of intelligence, We think by randomly sampling people that those will kind of even out in the long run. But like I said before, it's a difficult procedure, and we really need to be very firm about the process that we use and making sure that each person has an equal chance of being selected into the sample. Now the second box, representative, this is a little bit of a spin on that. So in this case, we're selecting a sample in which members are purposely selected to create a sample that represents the population based on some characteristic of interest. So for example, if you think about College of St. Mary as our population, College of St. Mary is primarily made up of female students. So we do admit men into the graduate programs, but overall the student body, the vast majority of it is female. So if we were to do a representative sample, we'd want to make sure that those proportions of men and women are roughly equal to what the actual population of the whole college looks like. So same thing if you're thinking about education, sampling from different school districts, sampling from different ethnic groups, you would want your sample to roughly mirror that of the larger underlying population. So again, this sounds like a really good sampling method because we're really ensuring that it looks like the population, that we have that good generalizability. But at the same time, this can be expensive and time consuming to make sure that you're recruiting enough people that fulfill those demographic characteristics of interest. So the final one on the far right here in the red box is convenience sampling. And unfortunately, this is kind of what we're stuck with when we are talking about social science, education, or medical research. So in this case, we're selecting our sample based on ease of access or availability. So especially in my field of psychology, a great deal of our research participants come from college students who need extra credit. So we ask for volunteers, we give extra credit. Sometimes we pay participants a small amount of money to participate in our studies, but we're really kind of looking for volunteers and people who are easily available. So this method obviously has its pros and cons. If you think about college students, think to yourself whether or not they're representative of the general population of everyone in the world. They tend to be more well educated. If we're offering extra credit, it usually means they're either doing very well in class and want that A+, or maybe they're struggling and could use some extra bonus points. But it may or may not be a good representation of whatever that larger population of interest is. So again, these are just 3 methods, kind of the most common that are discussed in your book, and there's definite kind of pros and cons to to all 3 of these methods. You can see there's a bit of a trade-off where it comes to accuracy versus ease of use. One way that we get around this limitation of the convenience sample, as I said before, it really impedes our ability to generalize or to apply those findings from one sample to another. And one way that we get around this in our convenience sample is to replicate our studies. So I might do a study with one set of students at a college in exchange for extra credit, and I may find that a certain study method seems to improve their grade. That's great, but I don't know for a fact whether or not that's going to generalize to all college students or all people that are learning something. So the way to get around this is I could replicate this either with a different group of students, a group of students in another university the following year, another time, another part of the country. The more that we're able to replicate our studies, the more confident we are in that ability to generalize back to that larger population. So this is why a lot of times when you're reading articles, you'll see that it might be an extension of a previous study or a replication with maybe a new twist on it. It's unusual to see just a straight replication, but you do see them on occasion. But the idea is that we're building on kind of our knowledge base and we're really growing the science and learning more about this phenomenon that we're interested in. To change gears a little bit now, I want to say a little bit about random assignment. So this isn't really mentioned in chapters 4 and 5, but I think it's an important distinction to make when we're having the discussion about random sampling or different sampling methods. So, excuse me, sampling methods refer to how we obtain participants from the general population to participate in our study. Random assignment is kind of the next step in that. So once I have my sample, how do I assign people in my sample to different groups? So whereas random sampling or selection is really hard to use, this idea of random assignment is kind of a workaround, and it's pretty frequently used. So you can see here the definition says that all participants have an equal chance of being assigned to any level of the independent variable. So if we take an example like our example of testing a new drug, and we have a drug treatment group and then we have a placebo group, we have two conditions or two levels of my independent variable. They're either getting the drug or the placebo. There's only two options. So I might use a convenience sample and ask for volunteers to participate in my drug study. I might pay them a small amount of money to try to get them. I might bribe them with food if they're college students. So I may use a convenience sample, but once I have my sample kind of recruited, I can use random assignment to assign them to either the drug or no drug condition. And this is a good example why you probably wouldn't want to ask for volunteers, because no one's going to volunteer to be in the placebo group, right? They all want to try the drug and see if it works and helps ease their symptoms. But the idea is, just like random sampling, that I would make sure that all of my participants have an equal chance of being assigned. So whether it's using a random number generator, whether it's flipping a coin, but I'd want to make sure that it's truly random and systematic. I wouldn't want to ask for volunteers. I wouldn't want to assign them based on some other factor. So this idea of random assignment can be really helpful when we're running experiments to make sure that even if our sample isn't random, we are randomly assigning people to experimental conditions. This slide has a couple of examples and really asking the question whether you can use random assignment and random sampling in any of these. So let's look at a couple of them. This first example, number 1, reads that a health psychologist is interested in whether post-operative recovery time is less among patients who received counseling prior to surgery than those who did not. So if we think about the general population in this case is people who are having surgery of some kind, how would I get people from that population into my sample? I probably couldn't randomly select unless I had kind of a master list of patients, and maybe hospitals are able to do that. But this might be more of a convenience sample where I'm looking for volunteers who've recently undergone surgery and asking them to participate in my study. So you can see how it would be difficult to randomly sample or select from that population. However, this is a good example of how we could use random assignment. You can imagine I might be able to flip a coin and assign half the people in my sample to receive counseling, and the other half might be my control group and receive no counseling. So you can kind of see whether or not the random sampling works versus random assignment. So the second one on here, the head of a school board has asked a school psychologist whether children in the school system would perform better in their history classes if they used an interactive textbook on an iPad as opposed to a traditional textbook. So in this case, we have children in the school system, and we actually probably have really good records and some kind of master list of all these children. So in that case, you could have the whole list of all the kids in the school system, and you could use a random number table or a random number generator to pull out random children to either receive the iPad or the traditional textbook. So in this case, I think the random sampling could work. It might still be a little bit of a bear to administratively pull this off with logistics. But in theory, if you had kind of that master list of all possible children in the system, you could randomly select from that. Now, could you randomly assign the kids to either receive the iPad textbook or the traditional textbook? In this case, I think you could. You might break it up maybe by classroom, just so there's no kind of jealousy issues about, which kid gets which. But I think you could definitely use some random assignment to kind of divvy up the students once they're in your sample. So that's an example where you could perhaps use random sampling and assignment. So then this last one is wondering whether Olympic athletes were more likely to socialize with athletes from other countries if they're from Western versus Eastern countries. So in this case, our population are Olympic athletes from the 2006 Olympics. And I imagine there's some kind of registration process that goes into the Olympics, so they would have a list of all the athletes who are there. So if you have this list of athletes, I think you could randomly pick athletes from that general population to be in your sample. So in this case, random sampling would work. However, it says we're interested if they're more likely to socialize based on whether they're from a Western or Eastern country. So this is a good example of when random assignment doesn't really work. So I kind of have to rely in this case on where the person's from. They're either from a Western country or Eastern country. It's kind of like a pre-existing variable, and I wouldn't be able to randomly assign athletes to one of those two conditions. Same thing when you see studies that are interested in gender differences. We can't really randomly assign people to gender. Maybe we could, but it would be unethical. So a lot of times when random assignment doesn't work, it's because we're interested in an independent variable that is already kind of pre-existing. So something like gender, ethnicity, socioeconomic status. If you think of medical research, smokers versus non-smokers, we can't really ethically assign people to smoke for a period of time. So think about what variables you might be interested in and whether or not they're a good candidate for random assignment and whether or not you're able to use random sampling from your population. Next, I'd like to shift gears a little bit and talk about the normal distribution or the normal curve, which is the rest of chapter 4 in your textbook. So here we have a picture of a normal curve. It's sometimes called a bell-shaped curve. And the bell curve or the normal curve is really important, so much so that it gets its own chapter in the book, because this shape is really the basis for our inferential statistics. And we'll get a little bit more into why that's the case. But the reason is the general shape of this curve, we think, and when I say we, I mean kind of researchers and general research population, we think that this shape really kind of mirrors a lot of variables or things that we find in nature that we're interested in studying. So your book gives the example of IQ scores, the idea that this is a normal distribution. So you can imagine that some people are really probably in the extreme tail here on the right. They have a really high IQ, though they're off the charts genius level. Other people on the left side of this distribution are kind of lower. They may have an intellectual disability that they're really low in terms of their IQ score. But the vast majority of us in the general population fall somewhere in the middle. We're just kind of around that average IQ score. So a lot of different variables in nature we think follow this pattern. So things like personality traits. You can imagine some people are incredibly extroverted, some people are incredibly not, but the majority of us fall somewhere in the middle, around kind of that average. Things like height, weight, you can think of extreme cases on either end of the curve, but again, the bulk of the population is going to fall somewhere in kind of that middle section. So we think that the normal curve is found a lot in kind of different variables we're interested in, and therefore it has kind of some specific properties that make it the case that our inferential statistics are able to work. So if the previous slide was a picture of a nice normal distribution, here we have a couple of examples of what happens when our curve doesn't quite fit that nice symmetrical bell-shaped curve. So in the upper right-hand corner here, you can see our normal distribution of IQ scores. IQ tests are usually normed with a mean of 100. So you can see I could fold that curve right down the middle. It's beautifully symmetrical on either side. And again, a great example of that nice normal distribution. Kind of exhibit A and B here is what happens when we have what's called a skewed distribution. So what happens when our curve doesn't follow that nice normal pattern? This is something we want to be aware of because sometimes this can cause our statistical findings to be kind of altered, and if our data is very badly skewed, we might have to use a special type of statistic to get around that problem. One of the kind of major underlying assumptions of our statistics is that our data are following kind of this general normal distribution pattern. So you can see here exhibit A, we have an example of positive skew, and you can see we have some high scores that are pulling the tail far to the right, and it's distorting the shape of our normal curve. And you can see here that the mean is actually being pulled up normal than it would be. So that might be an example of, say, Warren Buffett's annual income combined with everyone else in the Omaha, Nebraska area. That really high value is going to skew that mean and pull it upwards. Similarly, exhibit B, we have negative skew, and in this case we maybe have an extreme value on the low end that's pulling the tail of the curve to the left or towards the negative direction. And you can see similarly the mean is being pulled downward. So if you think of something like a class of students, maybe the course is based on 100%, and you have someone who hasn't showed up and done any of the assignments and has a 0, that's going to negatively skew your data and your curve, and it's going to pull those values towards the negative end. A second factor that might affect how our normal curve looks is this idea of kurtosis. So kurtosis refers to the shape of the distribution in terms of its height or flatness. So you can see a couple of examples here how that shape of the curve might change as well. So that yellow curve there you can see is much flatter, and it's kind of pushing the tails out and making a flatter curve versus the blue curve that's really kind of high. The scores are going to be really tightly clustered around the mean. So both skew and kurtosis are things we want to be aware of because, again, kind of that underlying assumption of our statistical tests is that we have normal or appropriate levels of both skew and kurtosis, and meaning that our data roughly mirror that normal curve shape. So another thing that affects the normal curve, and this will become really important when we start running our statistics, is sample size. So in general, as our sample size increases, the shape of our distribution becomes more like that normal curve. So as I said before, there's lots of variables that tend to be normally distributed. One thing to consider is whether or not nominal or categorical variables can be normally distributed. So something like gender that maybe only has 2 values, if you were to plot that in a curve, it's definitely not going to follow that normal shape. So there are limitations to the normal curve and kind of what we can do with it. But as a general rule of thumb, if we're looking at variables that we believe to be normally distributed, generally the larger the sample size we have, the better, because our data is going to more closely represent that normal curve. So I have here a link to a website called Math is Fun. You can't beat that for a website title. So I just want to do a quick demo here to kind of visualize why sample size is so important when it comes to our statistics. Okay, so here we have mathisfun.com. Don't be fooled by the somewhat cheesy layout of the website. It's actually a pretty useful resource, and I really like this as a good illustration of the normal curve, but this is what's called a virtual quincunx, or if you've ever watched The Price is Right, I think of this as Plinko. So if you're familiar with Plinko, you maybe drop the Plinko chip or a ping pong ball, and it goes down these different pegs. And basically you have a 50-50 shot of either going to the left or the right of each peg. And if you've ever played Plinko or maybe seen this at a carnival, you know that the really good prizes are on the far tails of the triangle. So either the far left or the far right. And you can see here as my ping pong balls are dropping, it's plotting the results in this bar graph in terms of what slot the balls are dropping into. So I'm going to increase the speed of this just a little bit and we'll see what happens. Let's drop the speed way up here. So you notice that the bars that are growing the quickest tend to be those ones in the middle. And you can see it's telling us right here how many ping pong balls we've dropped so far. So pay attention to kind of these outer corners of the game board to see how long it takes for us to land in one of those. And as you can imagine, if you think about this from a probability standpoint, to land in the far right corner, you have a 50-50 chance of either going left or right on each peg, and you'd have to go to the right every single time. So probability-wise, that's pretty unusual, and that's why when you go to a carnival now, you're going to be a very wise consumer and know that winning those prizes in the far corners is actually really difficult. So you can see here we're coming up on dropping 100 ping pong balls, and we still haven't reached those corners of the distribution yet. So the idea is if we keep letting this run for a while, eventually, from a probability perspective, we're going to hit some of those prizes, or we're going to hit those far ends of the distribution. Let's see if we really max it up on here. So one, it's meant to be a cautionary tale of when you go to the carnival and if your kids want to play one of these games. Oh, we got one in the corner there. But two, it's a really nice representation of why sample size is so important in statistics. So we want to make sure when we're sampling that we're getting enough people that kind of adequately represent that underlying population. So that includes kind of the full spectrum of possible values, as we can see here on our imaginary Plinko board. So feel free to play around with this on your own time. You can amaze all of your friends with your knowledge of Plinko and probability and carnival games. So returning to our slides here, to sum up Chapter 4, they talk a little bit about, at the end of Chapter 4, about how the normal curve can be divided up into proportional areas using standard deviation. And ultimately, we can use these to determine percentiles. So that's a really good segue into Chapter 5, where we're going to talk about standardization, z-scores, and how those z-scores fit onto the normal curve. Chapter 5 gets into standardization, z-scores, and how this relates to the normal curve. And really the reason why we're interested in this idea of standardization is because it allows us to make comparisons across different variables that might be measured on different metrics. So if you think of something like height and weight, those are measured differently. We might measure height in inches or feet, and we might measure weight in pounds. And we would actually be able to make comparisons on those variables by using a standardization. So kind of the first step in doing this, we need a couple of pieces of information in order to calculate something called a z-score. And you can see here we have our z-score formula. And I'm not going to get too far into the formula. In my opinion, the book goes a little nitty-gritty in the calculations, but I want you to understand conceptually what this formula is telling us. So we have here that z equals, and on the top part of the equation, we have x, which is going to be someone's raw score. So if we're going with the example of height, it's whatever my height might be, my individual score on any variable. Minus, you see here we have the Greek letter mu, and that means the average or the mean. In this case, we'll still go with height. And on the bottom of this equation, we have the Greek letter sigma, which represents the standard deviation. So if I wanted to compute a z-score of my height, I would need to take my individual height, x, subtract the group height from whatever my population comparison is. Maybe it's the height of all women in the United States. We could get that data from maybe the CDC. So take my height, subtract the average height of all women, and divide by the standard deviation. And that would give me a standardized score, or a z-score. A z-score is sometimes called a standard score, and really the purpose is to help us understand where a score lies in relation to other scores in a distribution. And really it's telling us how far above or below the mean a given score is in terms of standard deviation units. So again, going back to the formula on the previous page, it's really telling me how does my height compare to the average woman in the United States in terms of standard deviation units. Here we have a picture of the normal curve with some z-scores or standardized scores drawn into it. So whenever we create this z distribution on the normal curve, the middle point or the mean is always going to be a z-score of 0. So if my height was exactly equal to the average height, the average woman in America, I would end up with a z-score of 0 because my height would be equal to the mean. So it kind of centers the distribution, and then you can see a z-score of 1, either positive or negative, represents one standard deviation above or below the mean. So the sign of my z-score, when you calculate it out using that formula, if it's negative, it's telling me that my score is below the average. If it's positive, it's telling me I'm above the average. And how big the score is, or the magnitude of that number, tells me how far above or below the average I am. So as an example, when we talk about outliers, we give a definition of an outlier of saying that it's a z-score that's either larger than a positive 3 or larger than a negative 3. So if you think about that magnitude, once we get into that range, we're really getting into the tails of the distribution. So in general, we care about the sign of the z, so whether it's positive or negative, and then how large that number is. To transform a raw or individual score into a z-score, again, there's a couple steps going back to that formula. So there's some good examples in your text. There's one on page 46 that talks about SAT scores, and I would encourage you to kind of walk through and make sure that makes sense. But let's think about just a really simple example that we don't even really need the formula for. Let's say that I'm giving an exam and the class average is a 70%. And I calculate the class standard deviation to be 10 points. So let's say that if I score an 80%, I could plug in that 80 for my x value here, subtract the class mean of 70, and divide by the class standard deviation of 10. And that would give me a z-score of positive 1. So that makes sense because I'm above the mean, because we know 80 is better than 70. My z-score is positive, so that's reinforcing that idea. And I'm above the mean by one standard deviation unit, or in this case, 10 points. Same thing, let's say I scored a 60, subtract the class mean of 70, divide by the class standard deviation of 10. That would give me a z-score of negative 1, meaning that I'm below the mean by one standard deviation unit, or by 10 points. So that's kind of an easy example because they're nice round numbers, but you could really do this process with anything, and well, actually for your homework you'll do this using SPSS, so we won't even have to deal with using these formulas here. Just kind of a note as an FYI, you can also work backwards through the power of algebra. So if you already have a z-score and you'd like to convert it back into a raw score, you can do that by just changing the formula. So you can see I've transformed it here, so now I'm solving for x, or the raw score, and I need to know my z-score, the standard deviation, and the population mean in order to calculate that. So you can go forward, you can go backward. Again, we're not going to do this by hand, we'll use the computer program, but really it's having that conceptual understanding of what the z-score means and why it's important. So again, the reason why we care about z-scores is because it allows us to compare individual scores on two variables. And really when we go to run our statistics down the road, SPSS is making this conversion in the background of its calculations. So it's allowing us to compare things that we normally wouldn't be able to. So if I wanted to look at the relationship between age and IQ, between height and weight, between self-esteem and intelligence, between classroom performance and self-efficacy, any of those variables that are measured on different scales, I'll be able to compare them kind of using this z-score process. Now I would bet if you asked any of your friends or family or someone on the street, they've probably not heard of a z-score, but I imagine if you ask them, they have heard of percentiles. So when we talk about things like standardized testing, so the SAT or ACT that are common here, a lot of times we ask students what percentile they scored in. So if they scored in the 95th percentile, that means they did better than 95% of all the other students who took that test that year. Similarly, in healthcare, a lot of times people will talk about newborn babies, what percentile they're in for height or weight. I think they even do things like head size, which is kind of an interesting one. But it's a way of knowing where a particular individual falls in terms of this distribution. So where they fall along those percentiles, how much better or worse they are compared to the rest of the population. So z-scores tell us where the value fits, and then based on that information, there's certain rules about where the z-score value will fall and how it relates to a specific percentile rank. So you can actually use the area under the normal curve to calculate a percentile once you know the z-score. Here's an example of the normal curve with some percentiles drawn in that correspond to the z-scores. So when I took statistics as an undergraduate, I learned this as the 68-95 rule. And what that means is that 68% of the people under our curve are going to fall between -1 and +1 standard deviations. And you can see there we have 34% on either side. Add that up, we get 68%. About 95% of the people under the normal curve are going to fall between -2 and +2 on our standard deviations or z-scores. So that leaves us with that remaining about 4% or so in those extreme tails. And you can see on this particular graph that the curve kind of maxes out at -3 and +3. And I mentioned earlier that generally we use that as a criteria for determining whether or not a score is an outlier, if it has that score that z-score larger than +3 or larger than -3. So you can see here the line goes perfectly down the middle. So 50% of the people in this curve will be above the mean, 50% will be below the mean. And you can further break that down with these percentages, the 34%, 14, and so on. So your book, I said before, goes into a lot of detail because there's actually a table in the back of the book that gives you even more detail about the different percentiles, all of those spaces in between. So it would allow you to be very precise and look up, say, a z-score of 1.12. What would be the corresponding percentile? So the end of chapter 5 gets a little in the weeds, in my opinion, in terms of calculating that and looking up those percentiles. It's interesting, and if it helps you conceptually understand it, definitely walk through some of those examples. But for the purpose of this class and our homework, we're going to look at SPSS. But again, understanding kind of the normal curve, why it's important, and how it relates to z-scores and percentiles is really going to set us up for next week when we head into hypothesis testing. So really where we're going with our hypothesis testing is what happens when we run into people who are in those extreme tails of the curve, who are in those outer 2%. And that's going to help us develop criteria for testing our hypotheses when we get into actually running some of the tests. So that's where we're headed. Again, if anything's a little unclear, feel free to reach out. I'll clarify the best that I can. I know we're still in kind of the vocabulary stage. We haven't gotten into hypothesis testing yet, but that's where we're headed. So if anything's still unclear at this point, definitely reach out, and I'll post a couple other resources that will help illustrate some of these points if you have any questions. So that's what we have for now. Thanks for listening, and we'll see you next time.